going to look at growth and decay, and we're looking specifically at exponential growth and decay. When we talk about exponential growth and decay, we're going to be using this type of formula or function, and it looks very similar to our continuous compounding type of formula. The difference is that we've just changed the letters, and we can use different letters because we can use the A is equal to P times E raised to the RT. We can also use Q of T is equal to Q sub 0 E to the KT. K is just our growth factor. That's the rate at which we grow or decay. Q sub 0, Y sub 0, those are just our initial values. How much we start with. Remember, our P was how much we deposited or how much we borrowed, our initial amounts. Our Q of T is our ending value after so many years. Same thing, okay? Now, if we have a positive K, a positive rate, we are going to grow. If we have a negative rate, we're going to decay. So if our K is positive, we are increasing. So we've got this increasing here. If our K is negative, we're decreasing. We're decaying. So let's look at a few examples of how we would put these together and solve, because sometimes we may need to solve for our K, solve for our rate. So suppose that at 19 years old, you win $100,000 for playing the lottery. If you would like to have $1 million when you retire at age 67, determine the average rate of return needed under continuous compounding. So basically, we're using this continuous compounding formula. We're starting with $100,000. Afterwards, at our retirement, we want $1 million. Well, the time, it's not going to be 67 years from now, because that's how old we want to be. We're currently 19, supposing. So we're going to take 67 minus our 19, and so that's 48 years later. So that is our time that we're looking at. So I need to know what our K or our R is. And so I'm going to put it into this formula right here. So I'm going to have $1 million is equal to $100,000 times E. I do not know what my R is, times my T. And we're going to solve. So in order to solve for that R, remember that these two things are multiplied. So I need to divide both sides by that $100,000. And so whenever I divide 1 million by $100,000, if you think about it, you have 5 zeros. So I'm going to take 5 zeros out, 5 zeros out, and I'm going to be left with 10, or you can do that on your calculator, either way, is equal to E raised to the 48 times R, because this is multiplied as well. I need to get this R out of the exponent, I have an e, so in order to get it out of the exponent, remember, we're going to take the natural log of both sides. And when I do this, natural log of e raised to the 48r, remember that we have the understood base of e anytime we have the natural log. And anytime I take the natural log of e, the rule is that it divides out and becomes just our exponent. So I get 48r. And we have natural log of 10. And so we divide both sides by the 48. And I do this calculation. Be careful in your calculators to do natural log of 10, then divide by 48. When you do this, you are going to get something that looks like a 0.04797. We're wanting an average rate of return. So I'm going to take the 0.04797 because we're talking about percentages. I'm going to take that and multiply that by 100 because remember this is the decimal format and I want to put it in percentage. And so that would be a 4.797%. And usually we want to round that to one decimal place. And so that would be a 4.8%. So we need a 4.8% return, average rate of return on this continuous compounding. Let's look at another example. We're going to look at this one according to a study published in 2012. Burmese pythons are becoming the new top predator in the Florida Everglades. Not many animals in the Everglades can stand against the python that can grow to 23 feet and weigh over 200 pounds. So 20 pythons were recorded as captured or killed in 1995. By 2009, that number had increased to 378. Write a function of the form P of t is equal to P0 e raised to the RT to represent the number of pythons captured or killed t years after 1995. So our t equal to 0 is going to represent 1995. So that means if we look at t is equal to 1, that would represent 1996. Because t is the number of years after 1995. Now we started in 1995 with 20 pythons. So that means our p sub 0 is 20. That was our initial amount. That's how much we started with. By 2009, that number had increased to 378. So we're talking 2009. So I'm going to do 2009 minus 1995. That's going to be 14 years. So I'm going to say P of 14, because that's 14 years, is equal to 378. I need to find that R, because I don't know what my rate is. But I do know these other numbers. So I'm going to have 378 is equal to my initial amount times E. I don't know what my R is, but I do know what the time was for this 378. That was after 14 years. And then I'm going to solve for that time. Very similar to how I solved for the R in the previous one. I'm going to solve for that time here. So I'm going to divide both sides by 20. I take 378 and divide by 20. And I'm going to get the 18 18.9 is equal to e raised to the 14r. I take the natural log of both sides, and when I do so, remember that this is going to go away and leave me with just a 14r, and I have the natural log of 18.9, and then I divide both sides by the 14. So I'm going to come up here, and I'm going to have natural log of 18.9 divided by 14 is equal to my r. So the natural log of 18.9 divided by 14. So that means that r is going to be a 0.20994, and we'll just keep two decimal places in this case, 0.21. So that's my r. It tells me I want to write the function. So here's the thing. When I write the function, I want it p of t because I want to be able to plug in any t value in here. I need to keep that initial amount, 20, e, my r is 0.21, and I'm going to leave my t. So my function in terms of t will be this. Anytime that you need to write a function, you're going to have the t or an x left. You're not going to use that final amount anymore. You will use your r, and you will use your initial amount.